Hello and welcome. Let's get started. Today we are going to continue where we left off, working on the C buffer overflow. We had written a Hello World application in C as well as Rust. Then we took the next step in the Rust manual, which was to make a guessing game, which requests user input. Knowing what we know about C, we can do some fun stuff. And then we're going to see how well that ports over to our Rust implementation. I already suspect it's not going to work real well, and we're not going to have a lot of success with it. But I would like to see, similar to our C implementation, how contrived an implementation we can achieve, such that we are able to knock it over and overwrite some things in memory. I don't know if it's possible. It's Rust. It's something that I'm not intimately familiar with, but I hope to learn a lot more along the way, and perhaps you will too. So, without further ado, let's get our screen share going. We have where we left off yesterday was we used Metasploit's pattern create to make a pattern such that we were able to identify the offset at which we start to achieve a pattern match. So AA3, approaching this with fresh eyes has definitely benefited me. AA3A 1, 2, 3, 4, 5, 6, 7. Yeah. Because we achieved overwrite with this. $41, 40, 16, 90 plus 4 or times 4, we hit our knot sled, and then we landed on the 42s. Perhaps I need to look earlier in the input for some success, because the objective here is going to be getting from where we're at, which is at main C. We break it at main C, and we see the beginning of the application starts at the address 401,185 and continues to the address 401,020B. So we are trying to get to the authentication method to either bypass the authentication, or even better, supply it a valid input so that it returns and jump execution to the authentication function and allow it to complete, which would mean our program does what it's supposed to do. We haven't knocked it over. We've just interrupted the flow politely, changed the end state, and move forward. So looking at this, we have our hung fuzz host, which we haven't really done much with today over the last couple sessions, and then we have our clang host, which we have done a lot with. Let's try to vagrant up and see how successful we are. Yesterday we were not having success. It appeared that they were not, that Vagrant, for whatever reason, after an update, did not want to bring up the host correctly. It didn't want to interact with VirtualBox, none too much. So we've gotten beyond that, and we are now at the point where we should be able to take advantage of the host coming up in an automated fashion. Yes, it's starting. Should be able to hop into the host with our development environment and continue. Good. So Vagrant, SSH. We're hopping into our development environment. CD into our Vagrant projects. This one is guessing game. And there we have our exploit written out to a file. We have guessing game, main C, make file. So the idea is we can do this. We can go and read. We could run guessing game, and into that we can pump exploit. And then we get a safe return. So clearly it works there in that scenario. But thinking through this very carefully, our pattern match offset is 9. So we've been going about this the wrong way. Well, not the wrong way. We've been going about this one way, but it's not yielded the success that we're looking for quite yet. So here we had hello 8, and there is some question as to where it's, we're not supplying that number, and it is coming up with that on its own. So let's rearrange our, so 416 from 9, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7. So we have 407. Let's see. And we'll call that 41. So we'll have uppercase A. We'll have a not sled there. Okay, so that moves, that balances our equation. We've moved it over. So we have 47 plus 3. Well, let's break 4 out of here. So 7, 6, 5, 4. And then we add the 3. So shifting left again. We should have 7, 8, 9, 10. So 4, 10. We have the same exact outcome that we had before. So we moved our, we've moved our bytes around. So let's say we wanted to do something useful in these 4 bytes. So let's say we have, let's say we have Bravo Charlie, let's go look at our tables. Assembly restructure, exploit dev Linux, assembly exploit dev Linux. We are looking for, let's look at some of Peter's notes. Account. Yes, we need to spell that correctly. Knowledge is not an object, it is a flow indeed. So he has a good example there. Looking at what we're trying to achieve. So DFS, he's using Windows in this case. These are Windows debug commands, I believe, if memory serves. Yeah, if you're using Ollie debug, you're running an operating system called Microsoft Windows. So the difference is, yes, XP, SP1, etc. Zor. Where is our Linux? Do we have any Linux things here on your? Yeah, much of the tutorials are going to be focused on Windows. So let's go about the hard way. Gdebug. We are looking to capture debug Linux. We are looking to capture RSP. So we could fire off backtrace. This is useful information. So crash it. Wonderful. What about -ex backtrace? Right, there's no stack, it exited safely. So if we didn't catch it, let's say that we go to /x. So we use a string dead beef plus let's go take out the NOP sled and make it more crashable. So /x. It's going to be 41, capital A. Then we should have dead beef. It's 42 times 410. 408 should be accurate. There's our 8 again. 6. Okay. The first thing we want to do then is X. Oh, break main. Quotes around it. Break main plus or minus X. That's equal. No stack. We did that backwards. Whatever reason, we have garbage in our stack. I thought we had run it. No, we had we had stepped it. Instead of next, we need to let's see. We have run in the beginning. Break main X next X info stack X backtrace. So we have our okay. Break main next not being run. Break 30. Okay. Let's get our happy spaces. Two times. So 406 plus 9 is 415. Oh, we're short bytes. 16, 17, 18, 19, 20. So we need 10. Why are you not running right? Let's run. Enter a number, hello, and then the number 8. We don't have a crash here. Let's simplify our equation. What do we say it crashes at? 425. Let's look at the listing. We had break 30. We never hit it. Main never calls the function. Let's break at 25. Oh, we're running it before. Order of operations here. Set breakpoint, then run to breakpoint. Now we are suspending execution right at the point where it reads out our numbers. So let's run it without a breakpoint. We haven't crashed it. A. Make clean, make. I wonder if we are dealing with. That was our exploit file. We need to disable Linux, disable memory protection. And we are looking for. That'll do it. Okay. Okay. What if we run it with nothing? That's a core fault or segmentation fault. Yes, core dump. Okay. Echo. Let's rerun with our generated string. Paste. Fine. Uh, Visit the other way. Echo. Well, V pattern. Set paste. I copy paste. And then we cat it into cat pattern pipe dot slash guess game. So we get this string. No results. Okay. It goes ahead and reads us the last of the string. Okay, so if we wrap guessing game in gdebug, which is gdb and enter a number hello 8. So why are we getting that? Okay, run. So it does run. How do we get gdebug to use gdebug use input from file? Oh, there we go. Run pattern. There's our backtrace. So AC4D1B. That's a really high address. AC4D1 Bravo 7 Bravo is a pattern. Okay. Not show stack, it is info stack. That's what we got. Okay. Info, all registers. Info. Info, all dash registers. RSP, Echo 1, Charlie 0. So we are RSP Echo 1 Charlie 0. We're Echo 1 Charlie 0 into it. We're starting at a different base. Huh. Let's run exploit. So with the exploit we wrote, we got it to overwrite 42, 42, 42. So Linux execution, stack pointer, RSP, what is the 0th address? Next address. We're using user space. So this is user. That's a good point. We should be using object dump to review our DJ. Where is their text? That text. Versus BSS or data. Dash M Intel. we have a very contrived compilation. If we look at our make file, out. So where's my source file? It would be main.c, but I need an object file. So GCC output. So that'd be LD. Oh no, the C without linking and the O. Dash C. Is that correct? Yeah. So that'll give us an O instead of an executable. And then I wonder if I can run this twice. So I get both. Dot O. So make clean, make oh. I want, but I would also like, let's try our object. Right. So we are not outputting. Make clean. See? No. It would be guessing game. There we go. This should make more sense because we have authentication, which is totally separate, which begins further down up memory than so here's our main plus its offset. RBP, move. So push RBP, move RBP, move to RBP the stack pointer. So we just dumped whatever was in our by in BP RBP to another pile. Sub RSP and sub should be AMD 64. AMD Intel 64. There we go. Sub yep, it is what it is. Subtract 330 from whatever. Subtract 330 from our SP. Move the value at D word pointer RBP minus 04. So let's double check move. Move should be source destination source. Mov HIJKLM mov. So mov D word pointer so pointer RBP minus offset 4 move RBP. See, these are moving. Okay, offset 64. So we are looking at operand 1, operand 2. Copies the second operand, the source to the first to the destination. Yes, so they're reversed. The source operand can be an immediate value general purpose register. In this case, it's a destination register. So mov dword pointer RBP minus 4. Let's make sure we're thinking this through correctly. We're gonna move it from source to the destination, from right to left. We're the address at our RBP, and you saw that we took the stack pointer and moved it to RBP. So in BR64. So this is really the first in BR64. Not familiar with that one. Terminate an indirect branch. So F3O, F1 echo, FA. That's correct. An indirect branch is going to be our entry into the program. So It doesn't do anything. Op, Zio, NA, 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 NA. So it does nothing. It does nothing. Um, Other than it's a hard delimiter for the prior execution, which would have been when the shell did an int 80 to reach out to the um, when it called in 80 to reach out to the system and asked it to spawn the execution of this program. So we've entered the program at NBR64. We push RBP, push M mod RM decrement stack pointer and source operand on top of the stack. So our source in this case, because there is no dest in this operation, is the first stack operand RSP equals RSP minus 8. So we take 8 bytes away, and then we push our source on. Also have operand size 32. Also stack. Then finish. Okay. Then some rules regarding what triggers a page fault. Okay. So stop execution, push this RBP onto the stack and subtract 8. So we're overwriting the stack. Then we are moving our stack pointer to RBP. Then we are subtracting $330 from our RSP. So subtract RSP 330, which is going to move us further into the program. For example, we could make that we can manipulate that value by making the program have a longer more includes would make that move. So move dword pointer RBP minus 4 XX. So move string. Okay. Move C, D, E, F, G, H, I, J, K, L, off. There we go. So move. And there's move to from debug control. So we are moving. Let's look one more time at it. Move. We're moving a pointer we're moving 0 to this, whatever resolves the word pointer. RBP -4. So we're moving the quad into, yes. So what is that? Let's see what Google says. Move copies data from source to destination. This is the destination operand, a memory address. Yes. So our byte pointer -4 calculates the memory address by taking the value in RBP, subtracting 4 bytes. Then, so 32 bits or 4 bytes. And we're moving 0 to it. So that's wiping out the stack. Summary: the instruction stores the 32-bit value into the memory location that's 4 bytes below the address stored in RBP. So initializing local variable to 0. Int I equals 0. Yes. So thinking through this, we are initializing. Let's look at our C. We are we've stepped beyond our includes because we aren't executing anything. This is a text. This is the main function, right? So we moved beyond our includes, and we are into BR, which terminates the previous string. Push RBP. Move RSP to RBP. So move stack pointer, but don't change executions. Stack pointer sub RSP 330. So we're going to subtract from the stack pointer 330 hex. We're going to move dword pointer RBP -4. So the next stack location, 32 bitness, is getting nulled out. It will be 0. LEA. That's a condition. X1D. Less than equal rax rip plus. It should be LEA. Load effective address. Dumbass. Load effective address. Yes. We're using 64 bitness, so it should be. Well, no, not necessarily. LEA are racks. Yes, that's 64-bit register. RAX. So now our A register, if we're thinking 16-bitness, so 64 bits RAX, is our instruction pointer plus 0. So we are putting at racks, we at the RAX, we're putting our instruction pointer. And then we're going to move RDI. Our RDI is our, yes. RDI is where is PQR? RDI is one of our registers. What do we think of our register? Our register RDI. RDI. Purpose. Why am I missing it? Argument passing. Oh, destination index holds memory address of the destination location for data copies. Okay. So, reviewed by ABI used on Linux and other Unix licenses. RDA registers used for first integer pointer argument when the function is called. Destination index. That's what I'm thinking of. RDI, so Rax, RIP, plus O. Move, Rax, RDI, move. So we're clearing eeks. We call to alpha, so we are making a call out to the function that is at to alpha, which is, oh wait, no, we're not. It's not a, where are we doing? Call is not call. We're not thinking in terms of languages, we're thinking in terms of processors. So call, again, an instruction, call procedure. And where are we calling into? Call to alpha. It's going to be, we're calling to alpha is a 16-bit. So again, we're writing to the stack. Later in two types call, interprivilege level call and task switch. Yeah, we're not doing this craziness. We are doing a near call. So an intra-segment call. When executing near call, processor pushes the value of the EIP register, which contains the offset of the instruction following the call instruction on the stack for use later as a return instruction pointer. So we're saving out our state before we move on. It branches the address in the current code segment, specify the target operand. The target operand specifies either an absolute offset or code segment, offset based code segment, or relative offset. In this case, we are absolute or are we a relative call? Assign displacement relative to current EIP. Yes, and we can see it's conveniently said, hey, we're positive offset to alpha from where we're at. So again, we are LEA. If near call, then if near relative call, then if operand size 64, then temp dest, sig dest, rel 32, temp rip plus stack is not large enough for an 8-byte return address. Then we're done and we push IP. Otherwise, we push 8 bytes. If I rip tar- So the question is call 2A main plus 2A. Yay. So what's next after this? LEA, EFG, HIJK, LEA. Right, load effective address. So we made a call, and this call writes out our previous what's it, the stack pointer? Call near relative displacement to the next instruction. Call rel 16. Huh. And what opcode was it? Echo 8. So call relative displacement to the next instruction. It's a near call, which pushes the value of VIP, which says offset of the instruction following the call instruction onto the stack. So we have the next call in the stack. Then we're doing this load effective address. Computes the effective address of the second operand, source operand, source and first operand, destination operand. So 8 delta is the opcode /R. Echo 8, then we have 48, 8 delta 85, 60. So LEA racks. So we go to the A register and we put the byte pointer minus OX1A0. Then we clear, so now we've stored our call. So we made, let's recap. We've modified our stack. We've returned. We've suggested an address. We're calling to that address, swapping it into the stack. Then we store that in AX. We move the address in AX to RSI, and RSI is source index, 64-bit register, general, for string memory operations is the second integer argument in most function calls. Facilitates efficient data move MOV SB and pointer arithmetic. So Again, we're messing with the pointer, not the data in memory. Uh, let's see. So what do they call that RSI? Register source index. And we see here, we repeat this pattern. So we've done this move RDI racks, RSI racks, our instruction pointer plus 0, and move RDI racks, move ex 0. So again, we're writing out ex. We're going to call, and then our next address on the stack. Lee, RDX, RBP, again, an offset. And then our 330. So we have not done initialization of a value here yet. Oh, looking at our C again. It's not 190, is it? This calculator is miserable. We need 64-bit. No, we don't. It's hex. It's still hex. So our char number is 400. Int boolean 0 we did. Char number is 400. Int boolean 0. Let's look at that note again. We're using mov dword pointer. So is offset hex 330. $816. Nope. Yeah, it's 190. So we do not see our initialization of 190 anywhere in here, do we? No. It's going to be calling a value elsewhere. It's going to be calling into data. No, here it is. How far off are we? It's 416 because our null terminator. Yes, it's slash zero, but it's a numeric zero. GCC string allocation. Oh, longer strings. The standard string object internally manages a pointer to dynamically allocated memory on the heap. So we're not playing with stack. Oh, yes. When the string is decided to go out scope. So when we stopped our execution, when we manually advanced our execution to the authenticator portion, and we ran the code against it, what we were seeing was not making sense to me because we were not seeing the string is out of scope. We weren't thinking about that. We were not thinking about variables being scoped locally versus globally. Um, so our zero initialized integer that we're treating like a Boolean. If we look back here, our Boolean zero is in the global scope, which is why it was available here. Okay. We just are never calling into it. Currently working on an application for a low memory platform. There's a series of many short strings, 100,000 strings, 4 to 16 characters each. From standard string to const char to save memory. Oh, standard string is going to be bloated. Gave him an output of 4 bytes because it's an address, it's a pointer. It's not dereferenced. There's a lot of indirection. Comes down to the empty is a pointer. to one of these? And the answer is followed in memory by the actual string data. So, oh. So standard string is going to have at least 3 words of overhead for each string, plus any overhead for having higher capacity than length. It's going to be, there's also memory allocator doing lots of small allocations. So we are asking the abstraction to generate. We're using DL malloc more than likely. And we need to use malloc. String copy car star P ABD ABCD ABCD. 8 bytes, C out P, free P. Right, there's a null terminator. We're thinking of that. Oh. So this is what we're after. The reason their particular code, their particular limitation is crashing is because they're writing 9 characters. They're 8 characters plus the null byte into an area for 4 characters. Probably overwrite the administrative data stored for another chunk of memory that resides behind your chunk of data. This data is often stored in front of the memory chunks. When free tries to put your chunk into the free list, it can touch this administrative data and therefore stumble over an overwritten pointer, which is kind of what we did. We overwrote a pointer. This will crash. That's beautiful. Graceful behavior, yes. It's in a totally different location than the one indicated by memory dump. Interesting. Yes, that's what we're running into because we can't go to to 7FFFFF 0 42 42 42. It's not a valid address. It's no longer going to work. If you want to see where I was coming up with that, it was here. We had 0x000007 FFF 00 42 42 42. So we're not doing what I think we're doing. And we can see that's the zeroth item on the stack. It doesn't look like we've corrupted anything else. What the hell is that? I don't know why I clicked it. Okay, copy. So thinking through the rest of this, call 7 0, and then we leave and we return. Because if we look at our C, we don't have anything. We just call print with stuff and then we return. And we have our authentication, which is a series of comparisons. So compare. So this prepares the stack, EDI, does a compare with the next address on the stack, jump not equal AF, authentication plus 29. So 86. 0 0 0 0 0 0 86. Okay. Whoever that was deserves a shout out. I mean, brilliant idea. Brendan Gregg's blog. Very good. Very nice stuff. See, they are trying to fix core dumps. I am a, I am not. I'm trying to work with them though. Let's see what happens. So we look at the backtrace, and there's their stack. They're using a Python program. So parent to child, read bottoms up. PyMain, simpler something, PyVal code, frame, code, frame, code, frame. Yeah, 5 to 17 are Python internals, not super useful. Can't see the Python methods. The frame 4 is the curses library. Lib incurses W. So disassembled, and then call the function. Yeah, guessing game is not executable at this point. We could do LD. We could do LD. We could do LD options file. LD. What's our file name? Guessing game. Undefined reference to printf. Well, we can use our linker if we put more effort into it, but we are not. Well, no, no, we're not. That was a very prescient observation. Object dump is very useful there. Let's go ahead and back that up in our notes here. dump. So we have object dump. By using C dash C. Yeah, if I called this manually, that should do the same thing. Now if we go run our object dump, yeah, does the same thing. We have written this in makefile format. I wonder if there's a way that I can, because we know it's linking it and creating executable. I wonder if there is a great way that we can output GCC pipe grep. We're looking for object. Nope. There's not a word object in the help. Because pile and assemble but do not link. Save temps, I bet might do it. Let's try that. Yes, so that would get us the ability to object dump guessing game main.o. Okay, that's fair. We could also do save. One may use save temps, and then they may and reference the object file in obj dump direct. Okay. So we could say, for the sake of saying things, we could say that, and say above it, this being verbose, for the sake of ease of understanding the options. I return to this inevitably. The object output. File the link execute destroying temp files default saved. Where's my make file? So get out of my make file. And then we will enhance this by saying serves PRESURVs the object files for use with object dump object dump. Okay. Okay, now we should be able to run make clean. We'll lose guessing game, make. Guessing game runs. Okay. Now, if we knock it over, we have a better idea of it's going to take 400. We didn't leave 400 in. Yes, we did. It's going to take 400 plus 16 bytes. So 416. And the last couple bytes are okay. So then we get 8, whatever 8 is. we try 400, we won't receive anything. No, we still get 8. Oh, that's because we overrode it so soon in the... No. What the hell? I wonder if I did this backwards. Yeah, double quote it, print a single quote a times 4 so that it can't be overloaded. Should be the same either way. If I reversed it, single quotes does not allow for interpretation in bash of the substring. Yeah. That's fine. Interesting. Double quotes is a little more dangerous because it does allow for interpretation in bash. So if we said 416, we get that. Pass it into guessing game. So what have we said? Slash x90. It runs off the edge, hangs for a second, and then goes away gracefully. So if we did times 4, make it parenthetically happening, make it parenthetical time plus the parent slash x quoted, single quoted slash x. What do we say in our listing? Mm-hmm. EB10. What was the useful instruction to fire? Uh, probably move. So 4889 Echo 5. No. 4883 Echo Charlie 10. 4883 Echo Charlie 10. 4883 Echo Charlie 10. Plus, well, this no longer needs to be parenthetical, plus null terminator. Let's be behaved. plus the summation, plus the result of that. No? Plus, no. Here, plus. Forty-one times 380, 390. So 4, 5, 6, 7, 8, 5, 6, 7, 8, 10, 12. So 12, 16, 16, 12, 16, 12, 16, 12, 13, 14, 15, 4. Yes. So okay. Oh, that gets us to 416, 17, 18, 19, 20. So I need 5 plus 4 is 9. So I need 9 more. Uh, minus the null terminator. So 4 plus, may as well do it this way. 42 times 9 plus. That is what we expected to see there. I don't know that we need the null terminator. Segfault. So if we start backing this down to 8, 7, 6, 5. Illegal instruction. So that is illegal instruction. So Python 3 C print 90 times. So we have 4, 5, 6, 7, 8, 9, 8. So we have 12 plus 4, 12. So we got 416, 417, 418, 419, 20, 21. 421 times 421. By guessing. Ah, I see. I have done the fail. Close quote. But if we do it with 421 A's, We don't get illegal instruction or a core dump. 422. 423. 424. That did it. So that got us from illegal instruction to seg fault. So do I only have 2 useful bytes here? Is that what I'm really understanding? Because when we do 90 plus 234 slash x 4883 echo Charlie 10. Oh, right. I still want parens for code. Well, PEMDAS applies here, so we do our parentheses, we do our exponents, we do our multiplication, division, then add, subtract. This should render right. I'm just being pedantic by going in and telling it, no, you do this, then you do that. Thinking through the listing. We don't have a call out to authentication. That's what's really messing us up. I need to jump, or I need to do let's compile that. And let's run it. Four 25. 90s are valid instructions, so we have 41s to compensate. Seg fault. Yep, 421 is happy. Four 24 is the legal instruction. If I put a 90, plus I get seg fault, but if I subtract 1, I get 423. Should have no. 422. Right, because I gave it a 2 byte instruction. Okay. So we have a legal instruction. Uh, so now to see exactly where our illegal instruction should be placed, we go and give it this pattern. So now if we go pattern, legal instruction, we know it's 424. So if we go launch our Kali instance and we say Kali, what is the magic number? Use the pattern to generate the number. Kali, and we go back up, pattern create. We don't need help, we need length 424. So we take our 424 length pattern, we copy it, come over here to our 424 length. We're not writing a report, at least not this moment, so we don't necessarily need to be as particular as we need to with the documentation. We're not screenshotting this stuff either. And we need to. So we have Python 3. So we have this, which we can copy. We can echo into vi pattern 424. Paste. Paste. Remove carriage, turn escape, colon, WQ. So we have our pattern 424. So now we do cat pattern 424 pipe guessing game, and we need to debug it. Gdebug guessing game. X. What is the magic word? Run. Okay, so it told us bad credentials. Okay. Stepping back a moment, we did not have the function accessible at all, as we weren't calling it. We were defining it, and then we were never calling it. So bad credentials is correct. Backtrace. No stack. Before we run it, let's execute a break at 30. We don't have a break point set. Break 30. Okay. Info stack. Okay. That is an interesting fun point. I don't see anybody in the chat, which is fine. It's late at night. So G-debug, guessing game, break 30, X run X. What if we did next? X info stack. Program is not being run. What if we break it? 10 X run next. G-debug. Guessing game. File guessing. Game run pattern. What did we say that was? 424. Three A, 4A. Is that what I'm missing? Three A, 4A. 3A, 4A. 3 alpha, 4 alpha, 5 alpha, 6 alpha. 7 alpha. But they're escaped with this stupid freaking N. Why isn't N? Oh, it's an. Okay, so is that a string? Is that a. I see the pattern. And we are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Are we 14 characters into it? A4? No, 3A. So we are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We're 13 characters in. Let's double check this. Let's ask it. Length 424. Query is 3 alpha. Is it upper or lower? Three alpha upper. Three AA 4. Eleven. Okay, let's learn how to count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 3 alpha. That's where it begins. Three alpha, 4 alpha, 3 alpha, alpha, 4 alpha. So why am I getting every other character of it? The ends are consuming space. So we're seeing a string representation of memory. That can't be right. It's not. We're seeing a string representation of. Okay. Let's see what happens if we go back and we give it 11 times 11 plus the result is 422. That's too long. Too much gone. Segmentation fault. Legal instruction. So really I need 41 times 11 plus taken away from this. So plus float slash x 90 quote times 2 plus 400 of those. Okay. What if we go 401 and 1? marked. Because if we change it out for, these will be 43s, and this will be a 42. What the shit? That makes no sense. 404. Ten. Because that's 20. 410 is 11. So 421, 422. Four 23. Okay. Okay, we have very precise control over it now. So we shifted over. Legal instruction. Seg fault. We are so close. Okay, we are getting very confused. Or if we make these 90s, we get a seg fault. 90 times 1. Not worried about that. We have 9. Now we have 10. Yeah, and the math the whole bears out 424. Still seg fault. Illegal instruction. So 90. What's a printf to you? What would give you a printf? Looking back at our object file, What gives us printf? This. How do we get back down to size? So 1 byte, 2 byte, 3 byte, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bytes. Segfault. Is it Little Indian? Do I have to reverse this? Well, let's use this. Yes, it's Little Indian. Which, if you're not familiar, is where's the smallest byte first. So it would be A, B, B, C, C, D, D, etc. So I need to go work backwards through. So I need to reverse this. So the easiest way to do that is to read it backwards from above. So F F F F echo F 0650 no 0659 delta 884. Okay, I need to set up the stack to be able to do that. Couldn't I just do a long jump? Where is. Okay, call Lee. This is what we ran, but we need to run this first too. And it won't do our calls because they're null. We can't do that. They're bad. We need to run bad cars against this bad. User share Metasploit framework. Tools, exploit, find, bad cars, RB. Oh. I need to run bad cars first. No, I don't have the memory contents. Okay, that's a valid concern. Okay, it's late. I'll own that. Python 3, print 90. Print F hello byte code. Echo 8. Just looking again. Echo 8 zeros. You can't just call it. Zero is a bad character no matter what. Null is gonna stop whatever freakish copy we've got going. This may not be able to be exploited in this fashion because we have a couple of things that are working against us. We're limited in space and we're limited in characters that we can use to call it. It's not so easy as calling jump ESP. Uh, Jump ESP Linux alternative shell code. Yeah. We have a call. We have a jump. We could use an egg hunter, but we have not allocated enough space for us. Return libc. And we don't have any wrap gadgets. We have nothing in .text that will. We have C3, which is ret. C9, which is leave. They're only in there once now at the very end. 75 Alpha Foxtrot. Or 7514. Hmm. Yeah, those are going to require zeros. Hello. Ah, yes. We're not crafting our own shellcode. We are crafting our own shellcode in this scenario. Uh, we're also crafting our own executable, and we're crafting our own C, which means we could go back to the drawing board again and think a little bit more carefully about what we could ask the compiler to do that would give us a few useful returns. That's a thought. She uses string copy function. Yes, we're we're in the advanced section of this category. We're exploring different techniques so it does not have to have bad characters, and we're doing it in Linux. Um, and we're making it position independent. Yes, that's where I was suggesting we jump ESP. Excuse me. Jump ESP, but that is not something that's even in scope for this. We can overwrite return address. Yeah, that's in Windows. Very good thoughts. What did you have there? Local privilege escalation. Yeah, that's not an uncommon topic. Can't we use Zopcode? Not really. Yeah, we really want the address of a useful tool like Jump ESP. Overflow stack buffer, fill it with an op sled, your shellcode, and we overwrite the IP. So then the stack pointer points to the top of the stack. Processor begins executing malicious code. Yeah, we've used object dump and we've not found anything useful. Yes. Okay, we have hit a wall pretty hard. Register or shellcode, EIP jump call register, EIP points to register or shellcode. Register shellcode, EIP push register followed by ret. That's an interesting thought. Jump ESP. Yeah, that is one way to approach that. Okay. We input really long string will overflow the name buffer of right return address. We've done this. We've come to this conclusion. You know, that's a valid point. Okay, thank you, Stanford. B. Lin, whoever you may be. We're going to use this. Newer Linux version organizes the stack even more differently. That may be what I'm struggling with. Okay. Ben Lin out at crypto.stanford.edu. We're definitely making use of this when we return. Looks like that will be. Excuse me. Looks like that will be tomorrow. Tomorrow. Yes. as I have run out of whatever it is that allows me to continue past midnight. So it's almost midnight hacks today. Thinking through this, we may have some better luck with fresh eyes and a little bit more rest. So in the interim, thank you, folks. I appreciate your efforts and thank you for watching. Thank you for paying attention. Thank you for the questions and comments. I really appreciate those. Uh, I'm very excited to be celebrating this in this space. It's a beautiful space. There's move over. There's a plant, a tree of some sort. It has a woody stem. I guess it would be. I have no idea. I have no idea what plant that is. It's very fun. We are turn oriented programming. Good night. Thanks for joining. Okay, so we did find comments. Thank you. We really appreciate that. At any rate, we're going to wrap this up. We're signing off, and we will attack this tomorrow, and we'll have a little bit more space. I'm thinking, timing wise, let me look at the clock. It is going to be call time, so it will be before 5. So 4, 3, 2, 1. Let's say we'll aim to get started by 1 o'clock tomorrow. I may start a little bit earlier. I wouldn't want to commit to 10 o'clock. I want to have breakfast, so breakfast, lunch, brunch. So I figure we will aim for 1 till 5 tomorrow. With 5 as a hard stop because I have a 5:30. If you have any questions or suggestions, please feel free to reach out.